Okay, so let's say I tell you that you're driving at 50 miles per hour. And then I tell you you're driving 50 miles per hour north. Okay, so in the second piece of information, here, what is the difference between these two guys? There's direction, there's more information here. There's magnitude and direction. This quantity, this is called a velocity, and it is represented by a vector. It is a vector quantity. This is called speed, and you can specify, you can express this quantity using just one number, and this is called a scalar. Okay. So in physics, we'll study a lot of quantities that are either scalars or vectors. Okay, so speed is a scalar, pressure is a scalar, temperature, okay, and so on. All these quantities, all you need is one number to specify them. Okay. Then we'll study quantities that are vectors: velocity, acceleration, force, momentum, and so on. Okay. All right, so what this chapter is about is, so here are these quantities that are represented by vectors. Now, to specify a vector, how many numbers do you need? I'm sorry? Yeah, so you saw that here you needed two numbers. It turns out that in 2 dimensions, you need 2 numbers to specify a vector. In 3 dimensions, you need 3 numbers. In n dimensions, you need n numbers to specify a vector. Okay. All right, we won't worry about all of that. So here's a vector in 2 dimensions. Okay, you needed one number to specify the magnitude, and this other piece of information told you the direction. And so, for instance, so in 2 dimensions, if you choose this as your reference axis, if you're traveling in this direction, that north direction will be specified by this angle, 90 degrees. Okay, we adopt the convention that will measure angles from the x-axis, and positive angles are counterclockwise from the x-axis. Okay, so there's the number. All right, now I said that in 3 dimensions you need 3 numbers to specify the vector. What do you need the third number for? Yeah, so it turns out that in n dimensions, you need one number to specify the magnitude and n minus 1 numbers to specify the direction. Okay, so now let me show you in 3 dimensions how it would look. Okay, so for instance, so let's say your velocity vector is like that. Okay, so here's the convention. There's many ways to specify the direction of this vector. Okay, so one way is, okay, you take the projection of this vector on the xy plane. Okay, yeah. And this will be one angle, and this will be the other angle. Okay, to give you the direction of the vector. Okay, and again, there are other angles that you could use. Okay. So all right, so what I want you guys to know is that in 3 dimensions you need 3 numbers to specify a vector. Okay, to specify a scalar in 3 dimensions, how many numbers do you need? 1. To specify a scalar in n dimensions, how many numbers do you need? I'm sorry? Okay, to specify a scalar in n dimensions. In any number of dimensions, you need one. Okay? All right, so now we already know that this guy is a more complicated guy than this. This guy is a more complicated mathematical object. You need more numbers to specify. Okay? Now here's the deal. Anytime you learn about a new mathematical object, what do you learn? When you first learned about numbers, what did you learn? Counting. What did you learn to do with them? Add, subtract, multiply them. That's what this chapter is on. Okay? We'll learn to add, subtract, and multiply vectors.
No, we get the calculus in the calculus course.
I'm sorry?
I said, oh no, we get the calculus in the calculus course.
Okay, I still didn't understand you. Sorry.
It's not one, I was just making a joke.
Okay. All right. So we'll learn to add, subtract, and multiply vectors. All right. All right. So let's get on with it then. So vectors are represented by directed line segments. Okay. The length of the vector, what do you think it specifies? The magnitude. Okay. So that also specifies the magnitude. And then from the direction it's pointing in, you can get the angle. So here are two-dimensional vectors. Okay. Now, we haven't specified the units for this. This vector could be representing velocity. It could be representing acceleration. It could be representing force. We don't know what it represents. Okay. But if you're adding and subtracting vectors, you wouldn't add velocity to forces and so on. So you would add apples with apples and all that. Okay, so we'll get to all of that later. Okay, so vectors are represented by directed line segments. Here's the notation. We'll write vectors with the arrow on top. This, the absolute value of that with absolute signs, this represents the magnitude of the vector. Okay. All right. So now here's the first physical vector we'll define, a displacement vector. Okay, let's say you start at point A and go to point B. Let's say you walk along that path. Your displacement vector, the displacement vector, is a vector pointing from the starting point to the final point. So the displacement vector for this walk, and this walk are the same. Okay. How many different walks will have the same displacement vector?
All of them that start from A and end at B.
Yeah, so an infinite number of walks can have the same displacement vector. Okay. You go to the library and come back home, what is your displacement vector? I'm sorry? No, you go to the library and come back home. What's your displacement vector? Zero vector, not, okay? So if you went in, I'm sorry? Yeah. If you come back to your starting point, the displacement vector is from the starting and end points are the same, okay? Now, what I want to make sure is you understand that zero vector is not the same as the number 0. Okay? So in 3 dimensions, the 0 vectors would have 3 zeros to it. Okay? We'll come to the details of that. All right. So again, all we're learning is how to add, do mathematical operations with vectors. Okay? So let's understand some stuff, elementary stuff. Here's A. Vector A, and 2 times A, so let's look at this guy. What is this guy? See, 2 is a scalar, so hidden in this thing is a scalar multiplying a vector. But you intuitively know what 2A would mean. What would 2A mean? So it would mean a vector that's pointing the same direction as A, twice the length, that's all. Okay. Minus 2A is a vector pointed twice the length of A, pointing in the opposite direction. Okay. So the minus sign makes it point in the opposite direction. Okay. So you already intuitively knew a few things. Now, when you add scalars, 4 plus 5 is 9. Okay. Generally, when you add vectors, if you add a vector of 4 units long and 5 units long, you don't get a vector that's 9 units long. Okay. The only time that will happen is when? When is the only time that will happen? I'm sorry? When they point in the same direction. Okay? Very good. All right, so all right, here's another thing about vectors. If you have two vectors that have the same magnitude and the same direction, then they're equal. Okay? So it doesn't matter where you draw the vector. The starting point doesn't matter. So for instance, if you, as far as physics is concerned, if you're driving 50 miles an hour north on I-95 or 50 miles an hour north on US 1, your velocity is the same. Okay? All right, so two vectors that have the same magnitude and that are pointing in the same direction are equal to each other. Yeah. All right, now we'll show you. So again, what we want to learn is how to add, subtract vectors. Okay, so we'll show you how to graphically add vectors. Okay, this is good to know, to understand. Okay, so here's a vector A and a vector B, and we want to add the two. Remember, we said that we can move this vector anywhere, okay, as long as it's pointing in the same direction and it's got the same length, it's equal to that vector. Okay, so if you want to add these two vectors, what you do is you take B, the tail of B is drawn on the head of A, and the sum is from the tail of A to the head of B. Okay, that's how you add vectors. Okay? So that's the sum of A and B. Now, once you learn how to add two numbers, you know how to add an infinite number of numbers. You can keep adding numbers. Now, the same is true of vectors as well. Okay? So if you want to add multiple vectors, you keep doing the same rule. Draw A, draw B, C, D, E, and there's the resultant vector. The sum is from A to the last vector. All right, then the next property you would like to know is the following. Okay. Is this sum equal to this sum?
Yep.
Does the order of addition matter? No. So you would like to check that if that's true for vectors as well. Okay? And it turns out that it is true. Okay, so this is the kind of stuff we're doing. We're just checking mathematical properties of these objects. Okay. That's known as the commutative law. It doesn't matter the order of addition. Okay, 4 plus 5 is equal to 5 plus 4, and that's true for vectors as well. Okay. And here it is for just two vectors in diagrams. Here's A plus B, and here's B plus A, and the sum is the same, vector C. Okay. You're adding a bunch of vectors. It doesn't matter what order you add them. Okay, that was this thing that I just showed you. Okay, So this is known as the associative law, okay, and it's true for vector addition. Yep. This diagram shows you that. So B plus C, here's B plus C, which is that, and A plus B plus C is A plus B plus C there. A plus B is that, plus C is A plus B plus C. So you're getting the same result both ways. Okay, subtraction really is addition. All you have to do is define the negative of something. Okay, so for instance, A minus B is really A of plus minus B. So once you define the negative of a vector, then you know subtraction. Once you know addition, okay? So A minus B is just A plus of minus of B. Okay, so if that is vector B, there is negative B. And then you know how to add vectors. So A negative B is there. Yeah. We've already done this. What does it say? Scalar multiplication. What do you think that means? You're multiplying a vector by a scalar. Okay? So, so if this number is greater than 1, then you're making the vector bigger. If this number is smaller than 1, you're making it smaller. And if this number is negative, you're making it point in the opposite direction. Okay. So 3 times A is just a vector whose magnitude is 3 times the magnitude of the vector A. All right, so we did all of that. We've just done addition and subtraction right now. We'll do multiplication in a little bit, but we need a few tools for that. Okay. Multiplication is a little more complicated. Right, so let's develop tools for that. Again, we want to do algebra. You don't want to be drawing pictures all the time. Okay. So if you wanted to add these two guys via pictures, you would have to draw this to correct length to get an accurate answer, and we don't have the time for all of it. Okay. So you want to be able to add them algebraically. Okay. All right, so let's develop the tools for this. Okay, so these are special guys, unit vectors. Okay, what do you think that means? The length of these vectors is unity. The length of those vectors is 1. Okay. And in addition, they are dimensionless. Okay. So we're going to use those. What we mean by that is that way we can use those vectors when we want to write velocities, forces, momentum, and so on. These guys have no dimensions. Okay. So we'll get to that. All right. So unit vectors are vectors that have magnitude of 1. How many unit vectors are there in 3 dimensions?
3.
An infinite number. A unit vector can point in any direction. Okay? We will take 3 special unit vectors. Okay? One that points along the x-axis, we'll call it I. The one that points along the y-axis, we'll call it J. The one that points along the z-axis, we'll call it K. All right? All right. So for now, let's stick to 2D. Yeah. So the unit vector along the x-axis is I. The unit vector along y is j. Okay. 5I. What is this guy?
That's a unit vector.
Is it a scalar or a vector?
Vector with both directions.
Very good. So this is a scalar multiplying a vector, so it's a vector, and that vector is this vector, 5 times I, 5I. What is this guy? Scalar or a vector?
Vector.
Vector. Okay. Can you do this? This is a vector. This is a vector. You know how to add vectors. Okay. So let's do that. So there is 5I and there is 6j. Okay. And the sum of those two vectors is this vector. And let's give it a name. We'll call it A. Okay. So vector A is 5I plus 6j. Now this is a useful way of writing vectors, because if you learn how to write vectors like this, now you can add, subtract, multiply them easily. All right, so let's use some terminology. So here's a vector. We've written it in terms of these unit vectors. This is called the x component of the vector. This is called the y component of the vector. Okay. Okay, if vector A, so I'll say this slowly. If vector A is 4 units and vector B is 5 units, when will their sum be equal to 9 units, have magnitude 9 units?
When they're in the same direction.
When they're in the same direction. Okay, so let's do the following. So let me show you. Okay, so here are two vectors. Now let's add the two vectors, A plus B. Okay. Okay, this is a vector, this is a vector, and they are in the same direction. So the sum of those two will be just a vector whose magnitude is just the sum of their magnitudes. So you can add similar terms. So this would be 8I plus these two vectors are in the same direction, and so you can just add their magnitude. Okay. So 13j. Now this is the way to add vectors. Okay, very simple. Okay, so you guys understand? So the rule for adding vectors is you just add the components. Okay. So if you're dealing with three-dimensional vectors, Ax is the x component, so help me out with A plus B. All right, I got the first component. What is the y component? AY plus BYJ plus AZ plus BZK. All right, so now you know how to add vectors. Okay. what is this going to be? I'm sorry? That's right. So ax minus bx I plus ay minus byj plus az minus bz. Okay. Okay. Makes life a lot easier. Okay. You don't have to draw very accurately and so on. And in fact, this generalizes. So a plus 2b is equal to, now let's do it in 2 dimensions. You guys understanding this? Okay. So ax plus 2bx I plus ay plus 2by. Okay. All right. And so on. So let's say we want to add 3 vectors. So a 3b minus 2c. Okay, we are in 2 dimensions. Anybody want to help me out? What is the x component?
AX plus 3BX minus 2CX, and parentheses I. AY plus 3BY minus 2CY.
Mm-hmm. All right. So now you know how to add and subtract vectors using components. All right. All right, so vector A is written as the sum of these 2 vectors. This is the vector along the x-axis, vector along the y-axis. This is known as the x component. There is the y component. Now, in 2 dimensions, how many numbers do you need to specify the vector? To specify a vector? 2 numbers, okay? In 2 dimensions, 2 numbers, okay? So the magnitude and the angle. So the convention is the angle is measured counterclockwise from the x-axis. Okay, so you can specify the vector by specifying these 2 numbers, or you could also specify the vector by giving these 2 numbers, ax and ay. All right. Which has more information? Which pair has more information? I'm sorry? The one on the right? They all have the same information. In fact, you can pick any 2 numbers and they have the same information. You could pick theta, ax, ay, any 2 numbers. They have the same information. Okay. It's just that this information is in English, this is in Spanish. That's all. Okay. All right, so this is the component form, this is magnitude and direction. Okay. And so obviously there'll be situations where you have to translate from one language to another. And so you need formulae for that. And here are the relationships. Ax is a times cosine theta, and for these formulas, the angle theta is measured counterclockwise from the x-axis. Okay. Ay is a sine theta. Okay, so when you have the magnitude and direction and you want to find the components, these are the formulas you use. Okay. So you use this formula to go from here to there. And when you have the components, when you want to go from here to there, when you have components, then you use these formulas. Okay. So to find the magnitude, it's ax squared plus ay squared, square root of that. And the angle theta is tan inverse of ay minus ax. Okay. Now it turns out that this guy has 2 solutions. Okay. And so you'll have to be careful about picking the right angle theta. Okay. And we'll come to that when we solve problems. All right, so now we're dealing with 2 dimensions. Okay. AX, that's the X component, that's the Y component. And all this says is if both components are positive, then the vector is in the first quadrant. If the X component is negative and Y component is positive, then the vector is in the second quadrant. If both are negative, the vector is in the third quadrant, and so on. Okay. So you saw that when you want to add vectors, if you have the vectors in component form, then addition is very easy. So when we'll solve problems where we're adding vectors, they'll give you vectors. So the first thing you do is find the components of the vectors. Okay? Find the components, and then the sum of those two is just the sum of the components. Okay? So the X component of the resultant is that. The Y component of the resultant is that. Okay, so we use a lot of mathematics in physics. All laws are stated as mathematical statements. Okay? And here's the deal. So here's a relationship you'll see. What this is telling you this R vector is a position vector, and the subscript F telling you it's your final position. So let's say you go on a flight like this. This is your initial position, and that's your final position. Okay? So you start off here and you end up there. Oops. This is the initial position, and there's your final position. Okay. And those are vectors. Okay, I just drew a, and so okay, this relationship won't hold for this flight. In this flight, the acceleration is not constant. Okay. This equation is valid when the acceleration vector is constant. Okay. Anyway, don't worry about all of that. So whenever you see a statement like this, the first thing you want to check is, see, here's a vector on the left-hand side. What do you need on the right-hand side? A vector. Okay, you can't have a scalar. You can't equate a vector to a scalar. That's all you're checking. Okay, so this is a vector. That is a vector. Is this a vector? Velocity is a vector, time is a scalar. A scalar times a vector is a vector. Acceleration is a vector, time is a scalar, half is a scalar. This is a vector. Vector plus vector plus vector is a vector. Okay? So that passes that test. Okay? Now we'll do another test. Okay. So the next test we do is the following. This is a vector. Is this a vector? Yes, that's a vector too. All right. But is this equation correct? Okay. Well, the dimensions of this is velocity. The dimensions of this are length over time. This is acceleration, length over time squared. So the dimensions are not right. Okay, so this is not a good equation. Okay. So first you have to make sure that the quantities, again, you're not going to do this every day. We'll always deal with the correct equations. We're not going to throw you off balance or anything. Okay. So I'm going to just check this. This has dimensions of length, length over time times time, that's length. Okay. Length over time square times time square, that's length. Every one of them has the right term. Okay. So this is so here's another example of a possibility. Okay, this is what Einstein is most famous for. This is his general theory of relativity. Okay, what this equation tells you is, it tells you the curvature of space-time. This thing is, and this is energy and matter telling how space-time to curve. Okay, so right, so what Einstein says is, if Earth wasn't there, space-time would be flat. Earth told space-time how to curve. And that's what that equation is telling you. Okay? So this distribution of matter, so you see the distribution of all this stuff is telling space-time how to curve. That is that term. Okay, that term contains the location of the stars and all that kind of stuff. And all these terms tell you how the space-time is curving. Okay, so that's Einstein's equation. But anyway, the point again is these guys are something called tensors. Okay, they're more complicated objects than vectors. Okay. But just like the same rules apply here. If you have a vector here, you have to have the vector of the same dimension. If you have a tensor here, you have to have tensors of the same dimension. Yep.
So because the very top equation, there's time squared, that one makes it incorrect. Like not,
Which one? This one?
yeah, that makes
Yeah,
it
no. The dimension of this velocity is length over time.
Yeah,
Acceleration is length over time squared.
okay. So because it's square and the other one's time, it's just,
Yeah.
okay.
Yeah. This is an apple, that's an orange. All right, now we are ready to multiply vectors. Okay. Now, you already know that vectors are more complicated than scalars. How many ways can you multiply 4 and 5? Just once, one way. 4 and times 5 is 20. Okay. It turns out that you can multiply vectors a couple of different ways. Okay. And those different ways of multiplying vectors are useful in different situations. Okay. So the first one is called a dot product, or it's also called a scalar product. All right, why do you think it's called a scalar product? It turns out that the answer is a scalar. Okay, so you're taking two vectors, you're going to multiply them, and the answer will be a scalar. So you're taking two complicated objects and getting a simpler object. Okay, so here's the definition. Here's vector A, here's vector B. Okay, and here's the notation, that's where the name comes from. A dot B, this notation tells you how you're multiplying the vectors. Okay, so A dot B, and here's the definition, it's defined as the magnitude of A times the magnitude of B times cosine of the angle between the two vectors when they're drawn from the same point. This is a scalar, this is a scalar, that's a scalar. You multiply three scalars, you get a scalar. Okay, so you started off with two vectors and you got a scalar. Okay. So here's the definition in terms of the magnitudes, and here's the definition of the scalar product in terms of the components. AX times BX plus AY times BY plus AZ times BZ. Okay, scalar plus scalar plus scalar.
Visually in those diagrams,
Mm-hmm.
what is the answer of the dot product?
This number.
So those diagrams, they don't show like a visual
No,
representation.
so let's say if this is um, if this is 4 units, 5 units, 4 times 5, and let's say cosine theta is 0.5, 4 times 5 is 20, times 0.5 is 10. Yeah, yeah, you can't, there's nothing visual. Okay, so that's the definition of dot product. So here's where it'll come. So let's say you apply a force on a cart and you push it that distance, or let me do it like this. So let's say you're pushing a lawnmower and you push the lawnmower from here to there, and you want to know how much work you've done. The work you've done is F dot R. So there's F. That's how much work you've done. Okay. So when you apply that force through that distance, displacement R, that's the amount of work you've done. So if you push your lawnmower around your house and come back to your starting point, how much work have you done?
A lot.
Huh?
Probably a lot.
0. R is 0. R is the zero vector. Okay. Okay, so technically you've done 0 work. All right. So now we'll do the second definition of vector products. So the second way of multiplying is called a vector product, and as the name suggests, the answer is a vector. Okay. So, and it's also known as cross product, and it's written like this: A cross B, and the answer is a vector, C. Okay. So I'll just give you the definition, and you might come across it in various different ways. You'll probably deal with it in Calc 3, I think. Okay. Anyway. All right, so here's the vector. The magnitude of this vector is magnitude. Oh, well, this needs a diagram. Oh, okay. Yeah. Oh, yeah, here's the diagram. A, B, C. Okay. The magnitude of the cross product is the magnitude of A, B, and sine of the angle between A and B. Okay, so magnitude of C is magnitude of A, B, sine theta. Yeah. Now notice something. The direction of C. What is the direction of C? The direction of C is perpendicular to the plane containing A and B. So A and B are two vectors, and they'll define a plane. And C is perpendicular to the plane containing A and B. All right, so here's a plane. Here's this plane. What is the perpendicular direction to this plane? Up or down? Right?
Show it again.
Here's the plane A. Let's say this is the plane of A and B. What is perpendicular to this plane? This here's one perpendicular and there's another perpendicular. So now you got to figure out which direction is C pointing. Okay? And so here's the rule. And this is known as the right-hand screw rule. And what you want to do is, all right, so if it's A cross B, you turn from A to B. So if you turn a screw from A to B, so let's say this is A, this is B. If I turn A to B, if I turn a screw from A to B, which way will the screw move? So if I turn it from A to B, the screw will move in that direction.
C, yeah.
That's the direction of C. Okay? So that's how you figure it out. So that's known as the right-hand screw rule. Or you can point your thumb in the direction of A, the first vector. There's the second vector. Your middle finger points in the direction of C. Okay? But this is not that good because sometimes you're not able to turn your hands in the appropriate direction. So this rule is the one to remember. You turn a screw from A to B, and the direction in which the screw moves is the direction of C. Okay? All right. So you have the formula for the magnitude. You know how to figure out the direction of C. Okay. Now let's give you the vector form of C. Okay. So here's how you remember it. So I'm showing you one way of doing it. Again, okay. So A cross B. So the x component of C is AY BZ. The x component is AY BZ minus the opposite, AZ BY. Plus the jth component. The jth component is AZ BX minus AX BZ plus the kth component. The kth component is AX BY minus AY BX. Okay, so that's the definition of the cross product. And you just have to remember it. Yep. If you have had determinants, it turns out that it's equal to this determinant. Okay. Okay, so there's the definition of cross product. All right, so what we've done is we've learned how to add vectors, we've learned how to subtract vectors, and now we've learned how to multiply vectors. Okay. You will see this cross product when you calculate the torque of forces, and in physics too. If you have a charged particle moving in a magnetic field, the force on the charged particle is Q, the charge, V cross B. Okay, so there will be a couple of situations where you'll see these cross products. Okay. Now, 4 times 5 is equal to 5 times 4. It turns out that the cross product is anti-commutative. It's not like that. Okay? So A cross B is minus a B cross A. So A cross B, if this is the plane, and if A cross B is in this direction, B cross A is in the opposite direction. Okay? And there's the magnitude of A cross B. Okay? What is I? What is I?
X.
I'm sorry?
X.
It's a vector. It's a unit vector pointing in there. What is J?
A unit vector.
A unit vector. So there must be, you can define I cross J. So these are special cross products, and we want to remember this. I cross J is K, J cross K is I, K cross I is J. Okay, so these are special unit vectors. Special cross products that you want to remember. What is I cross K?
J.
Minus J. Okay, and so on. So this diagram shows you, okay, so I cross J is K, I cross J cross K is I, and so on. All right, so what we have learned is we've, again, like I said, we've learned to add, subtract, and multiply vectors. How many different ways have you learned how to multiply vectors? Two. Okay, you've learned how to get use scalar and vector products. Okay, and they'll both be useful when we learn physics concepts. We'll apply them later.